Well, as I mentioned before the break, apart from the usual, well, what is usual? Apart from the addition of spectra, there is a multiplication of spectra, and it's more complicated than addition. Well, something similar happens with numbers. Well, for example, integer numbers can be added and they can be multiplied. And if we just restrict ourselves to adding integer numbers, then then we get something which is complicated, but still tractable to some extent. If we allow multiplication in, then we get the arithmetic, and it's well, probably as complicated as it gets. Okay, so there are several ways to define the smash product. Let's firstly see what which properties we expect the smash product to have. Well, firstly, we want the smash product to be associative. At least in the homotypic category. So we want to have isomorphisms between the two ways of putting the parenthesis in the product, so that so that we get a monoidal structure on the homotypic category, at least. Actually, if I'm talking about a monoidal structure, I need a unit. So let me also require that the sphere spectrum should be the unit. The next thing we would like to have is a symmetric monoidal structure. So we would like to have an isomorphism between x smash y and y smash x. And lastly, we would like to we would like the smash product to distribute over the wedge sum. Is there anything else? Well, there may be other properties we we will need, but let's focus on the ones I've already stated. Let's see. So there are several ways to do the smash product on the level of spectra, which all give the same result in the homotypic category, but we will use the most naive construction that exists. Let me mention the others. So each of the constructions which gives us an associative and commutative product of spectra requires changing the definition of a spectrum, and for our purposes, it just doesn't seem to be worth it. So we will see the least fancy version available. Well, to begin with, let's let's notice the following thing. Observation. Well, suppose X is a CW spectrum. Well, recall that well, it is safe to get rid of all negative components with a point, or all components below a certain index with a point, because the homotopy groups are not affected by this operation. And furthermore, we can take two indices m less than n and replace all xi for m less than I less than n with sigma I minus m of xm. So this thing is inside sigma I. That may not be, but it may not coincide with all of sigma I. But this operation does not change does not change the homotopy groups. So we basically we're not interested in all xm or xi. We can just take a cofinite family and replace all the rest by suspension. Let me let me write this down. What does this mean? This means I apply this procedure not to one segment m less than n, but to infinitely many overlapping, non-overlapping segments. Does this make sense? Does the statement make sense? So once again, I take a spectrum. I choose some number of some cofinite family of indices, and I just keep the components which have those indices, and I replace everything that's between any two adjacent indices by some suspension. So my claim is this procedure does not affect the homotopy groups. Basically, what I get is a cofinal. The result is a cofinal spectrum. Does the statement make any sense? То есть мы берем какое-то кофинальное множество индексов и вот берем иксы с такими то есть берем вот компоненты, которые соответствуют этим индексам. А что происходит со всем остальным? А все остальное мы просто заменяем на настройку того, что мы можем настроить. Ну, какое-то количество клеток при этом теряется. Но каждая стабильная клетка, она при этом остается. Она, может быть, возникает позже, но она все равно возникает. Does this make sense? Okay, well, so far nothing happened. Let me give the first definition, the first attempt to define the product, the smash product. So the first version. Well, I just take x smash y to 2n as a space, I just take it equal xn smash yn. Well, I need to okay, so this gives me something defined for only even indices. Well, it doesn't matter if I'm able to construct the map from the double suspension to the next stage, then I can just take the intermediate component to be the suspension of this one. What do I do? Well, firstly, I can rewrite the space. And secondly, I rewrite it again. But this on the level of spaces, basically we have the this homeomorphism, and this is basically it. But please observe that we have swapped two elements in the product. We have swapped two factors, and there's this Koszul rule which says that every time we swap two things, there's a sign which appears, and the sign is -1 to the product of the degrees. Well, for some reason, the degree of S1, the degree of S1 is 1. No surprises there. But let me put the quotation marks. This is just a metaphor, not a proper definition of the degree of anything. So basically, we want the structure map to be -1 to the nth of this map. Now, what exactly is -1 to the nth? There's the leftmost S1. So if there is a -1 here, we invert the coordinate on the leftmost as 1. Does this make does the definition make sense? In order for us to get a spectrum, we don't actually need to do this. It would work either way. But for the properties we're after, we need this weird sign change. Does the construction make any sense? Alexei, Andrei, Juping, does this make sense? Okay. Well, now let's see if this definition works. Let's see what happens on the level of components when I take, for example, 4n. Well, I get x to n, wedge y n, wedge z n. And if I do it the other way around, I get 2n on the right, not on the left. Does everyone agree? Okay, so the definition gives us two results which are definitely not the same, although they are somehow similar. So what do we do? Well, we need to be more flexible. For example, here I take x to the n and y to the n, which have the same index. Well, maybe we should allow the indices to vary as long as they add up to the index here, and both go to infinity as this index goes to infinity. So, second version. So we take a co-final subset . well, for some reason I want to use beta of A wedge y gamma of A, where beta of A plus gamma of A is A for all A and capital A, and what? And beta and gamma go monotonic, not strictly monotonically, but monotonically to infinity. Let me write it down. For example, we could take let's first look at this definition and see if it makes any sense. This is somewhat more general than the first version. Basically, the first version would be to take A equal the set of all even numbers, and set beta of A equal gamma of A equal A 1/2. So we allow arbitrary functions beta and gamma. We can still define the structure maps basically using the same trick as here. Only in general we will have more factors S1 on the left. Так, Андрей, Алексей, имеет ли смысл происходящее? Okay. Now, let's see if this helps us to avoid having problems of this type. Of course, when when I define something which depends on a function beta and another function gamma, that's raises the question whether the result is independent of beta and gamma, and if it is, then how to compare the results of what happens if we replace beta with beta prime. We'll come to that later. Firstly, let's see if this helps. Well, it sort of helps if we're allowed to use some beta and gamma here, another beta and gamma here, you get possibly a different gamma and beta here, and something else altogether here. So there is for example, let's look at this product. My claim is I can choose. There are two smashes. Well, for example, for the exterior smash. So let me call this smash 1 and smash 2. For smash 1, I take A equal the set of all integers divisible by 3. Why? Because why not? And beta equal beta of A equal A by 3, and gamma of A equal 2/3 A. Very well. And for the second smash, I just use A equal even numbers, and I basically use the same recipe we used here. Okay, so so there is a way to define to use smash 1 and smash 2, so that the components with indices 3n become just the smashes of the components which have index n. And similarly here, there is a way to choose smash 1 and smash 3 and smash 4, so that we get the same result. Brilliant. Now so we have associativity, but we needed to make some arbitrary choices along the way. So if we prove that in the homotopy category these choices do not affect anything, then on the level of the homotopy category we will have associativity. Now, so this gives us associativity modulo the assumption that these choices that we made do not really do much in the homotopy category. Well. Let's see if the sphere spectrum is indeed the unit, just like what we expect. Okay, so here let me take A equal basically let me take let me make the same choices as in this example, and I get the. If I use those to define the smash with the sphere spectrum, what do I get? I get well, Sn smash 2nth component would be xn, sorry, Sn smash xn, which is sigma n xn. Okay, so well, let's first observe that sigma n xn is inside the I'm looking at the first smash, and I'm looking at the 2n component. And what do I get? Well, I don't get this quite the whole of x to n, but I get the suspension, the nth suspension of xn, which is inside x to n. So at least I have a map from this smash to x. So we get a map. And by what we saw a few times already, this map induces an isomorphism on the homotopy group. So the spectra are not the same. These two spectra are not the same, but there is a map from one to the other, which is an isomorphism in the homotopy category. Let's return to the other smash in a couple of minutes. How to, is it true? Is it not true that we have this isomorphism? Well, there is the question of science, which I mentioned already. We want to avoid this problem of science. Well, basically the easiest thing to do would be to take all numbers divisible by 4 instead of 2, and again beta of A gamma of A is 1/2 A. So we say that x wedge y for n is x to n y to n, and there's only even indices which participate in this construction. So this gives me a map from one spectrum to the other spectrum on the components which have the degree which have degree to 4n, and there will be so the map is more or less identical on these components, but this doesn't mean that it will look identical on the components between 4n and 4n plus 1. So we basically have all properties of that we need to ask the question whether or not the homotopy category of spectra will no, actually no. We so before we even ask whether the homotopy category of spectra is symmetric monoidal, we need to check that the construction does not depend on the construction does not depend on the choices we made for A and beta. And after we've done this, we will have an isomorphism in the homotopy category from here to here, the associativity isomorphism, the commutativity isomorphism, and we will need to check that in the homotopy category both combine to a symmetric monoidal structure. Well, let's do it next time. I think we're all we're all tired and tired of spectra, tired in general. So let's call it a day. Are there any questions?